Download this code from codegive.com, link in the description below. Using Silsafedata failure rate comparison for safety integrity level, SIL, verification. This tutorial delves into using Silsafedata failure rate comparison functionality to assess the suitability of components or subsystems for safety instrumented functions, sifs, and verify their safety integrity level, SIL, achievement. We'll cover the theoretical background, data sources, methodology, and provide a practical code example to illustrate the process. 1. Understanding safety instrumented systems, SIS, and SIL. Before we dive into failure rates, let's briefly review the context. Safety instrumented system, SIS, a system composed of sensors, logic solvers, and final elements designed to automatically implement safety functions when predefined hazardous conditions occur. Think of it as the automatic emergency shutdown system of a process plant. Safety instrumented function, SIF, a specific safety function implemented by the SIS. For example, shutting down a reactor when the temperature exceeds a critical threshold. Safety integrity level, SIL, a relative level of risk reduction provided by a SIF. SIL levels range from 1, lowest, to 4, highest, each corresponding to a specific probability of failure on demand, PFD. A higher SIL requires a lower PFD, indicating a more reliable system. Here's a general table. SIL probability of failure on demand, PFD, risk reduction factor, RRF. SIL 110 superscript 1 to 10 superscript 2 10 to 100. SIL 210 superscript 2 to 10 superscript 3 100 to 1000. SIL 310 superscript 3 to 10 1000 to 10,000. SIL 410 to 10 10,000 to 100,000. 2. The importance of failure rate data. Failure rate data is crucial for SIL verification. It allows engineers to calculate the PFD of a SIF, which is then compared to the target PFD dictated by the required SIL. Common failure rate metrics include lambda, lambda the failure rate, typically expressed in failures per hour, example failures/hour or failures/year. Often, this is split into lambda st, safe dangerous, and su, safe undetected. Lambda st, safe dangerous, the rate of failures that are both dangerous, cause a failure to perform the safety function, and safe, will cause the system to go to a known safe state and protect other equipment. Su, safe undetected, the rate of failures that are safe, will cause the system to go to a known safe state and protect other equipment, and undetected, not revealed by diagnostic testing or proof testing. These failures contribute to the overall dangerous undetected failure rate. (2) Dangerous undetected, the rate of failures that are both dangerous, cause a failure to perform the safety function, and undetected, not revealed by diagnostic testing or proof testing. This is the most critical failure rate for SIL verification as it directly impacts PFD. Lambda dd, dangerous detected, the rate of failures that are dangerous and detected by diagnostic testing or proof testing. These failures don't directly contribute to PFD because the system is alerted to the failure and can be repaired. PFDAVC, average probability of failure on demand, the average probability that the SIF will fail to perform its intended function when demanded. This is the primary metric used for SIL verification. MTBF, mean time between failures, the average time a device or system is expected to function without failure. MTBF equals 1/lambda, useful for reliability estimates, but not directly used for PFD calculation in the same way as do. MTTR, mean time to repair, the average time required to repair a failed component. This is crucial for calculating PFD, as longer repair times lead to higher PFD values. *DC, diagnostic coverage, the percentage of dangerous failures that are detected by diagnostics. A higher DC reduces the DO, as more failures are revealed and can be repaired. 3. Sources of failure rate data. Accurate failure rate data is paramount for reliable SIL verification. Here are common sources. Hazardous SERH database. A widely recognized and comprehensive database of failure rates for various components used in SIS. Exadata charges for access, but their data is often considered the gold standard. *TUV Rhineland *, another reputable organization that provides failure rate data and certification services. *ORDA database *, a database primarily used for the oil and gas industry. *manufacturer data * manufacturers of sensors, logic solvers, and final elements often provide failure rate data for their products. Be cautious and verify this data against other sources when possible. Look for certified values. Industry standards standards like IEC 61508 and IEC 61511 provide guidance on the use of failure rate data and suggest common values for certain component types. Field data collecting failure data from your own plant operations can be the most accurate, but requires significant effort and a robust data collection system. Silsafedata the focus of this tutorial. Silsafedata is a software tool that incorporates failure rate data from various sources to facilitate SIL verification. It allows you to compare data from different manufacturers and standards, and perform calculations to determine if your system meets the required SIL. 4. Silsafedata, failure rate comparison methodology. Silsafedata, assuming you have access to it, either through a subscription or demo, provides a user-friendly interface to 1. Component selection * choose the specific component you want to analyze, example pressure transmitter, solenoid valve, PLC. 2. Data source selection * select the data source you want to use, example Exadata, TUV, manufacturer data. Silsafedata ideally lets you load data from multiple sources into one place. 3. Failure rate retrieval * retrieve the failure rate data for the selected component from the chosen data source, broken down into DO, lambda DD, SU, lambda SD, etc. 4. Comparison * compare the failure rate data from different sources or manufacturers for the same component. This helps you identify potential discrepancies and make informed decisions. 5. SIL verification calculations * using the failure rate data, component architecture, proof test interval, and MTTR, calculate the PFDAV of the SIF. 6. SIL target comparison * compare the calculated PFDAV to the target PFDAV for the required SIL. If the calculated PFDAV is lower than the target PFDAV, the SIF meets the SIL requirement. 5. Illustrative code example, Python, conceptual. Since we don't have direct programmatic access to Silsafedata's database, this example simulates fetching and comparing failure rate data from hypothetical sources. It demonstrates the logic of data retrieval and comparison. This code is for illustrative purposes and needs to be adapted to a real-world scenario where you can access the failure rate data. Explanation of the code **** get _failure _data _source 1, component _name, and get _failure _data _source 2, component _name, ***. These are placeholder functions. In a real application, these would be replaced with code to interact with databases, APIs, or files containing the failure rate data from Silsafedata, if it exposes an API, or other sources. They return pandas data frames for easy manipulation. Data frames. Pandas data frames are used to store the failure rate data in a tabular format. Comparison. The code compares the lambda_do values from the two sources. A simple percentage difference is calculated to highlight significant discrepancies. In a real application, you might use more sophisticated statistical methods for comparison. Calculate_pdavg. This function provides a simplified pfdavg calculation for a single component, 1001 architecture. Real-world calculations are often more complex, taking into account the architecture of the sif, example 1002, 2003, and the diagnostic coverage. This calculation must be adjusted based on the requirements of your sif and the specific architecture and proof testing being utilized. *Sil target comparison. The calculated pfdavg is compared to the target pfdavg range for the desired sil level. This determines whether the sif meets the sil requirement. Important considerations and best practices. Data quality. Ensure the failure rate data you are using is accurate, reliable, and relevant to the specific application. Use data from reputable sources and consider the limitations of each data source. Understand the assumptions behind the data, example operating conditions, component age. Component architecture. The architecture of the sif, example 1001, 1002, 2003, significantly impacts the PFD calculation. Use appropriate formulas for the specific architecture. Calculate_pdavg in the example is a 1001 approximation. Proof testing. The proof test interval and proof test coverage are critical parameters in the PFD calculation. Develop a robust proof testing strategy and ensure it is implemented effectively. Common cause failures. CCF. Consider the potential for common cause failures, which can invalidate the independence assumptions underlying PFD calculations. Use techniques like diverse redundancy and separation to mitigate CCF. Beta factor modeling is often used. Human factors. Human errors during installation, maintenance, and operation can significantly impact the reliability of the sys. Implement procedures and training to minimize human errors. Environmental factors. Consider the impact of environmental factors, example temperature, vibration, corrosion, on component failure rates. Systematic errors. Address systematic errors in the design and implementation of the sys. Use a structured development process and conduct thorough hazard analyses. Conservative approach. When in doubt, use conservative assumptions and failure rate data to ensure that the sif meets the sil requirements. Documentation. Document all assumptions, data sources, calculations, and results for traceability and auditing purposes. Expert consultation. Consult with experienced safety engineers to ensure that the sil verification process is conducted correctly and that the sys meets the required level of safety integrity. Regular updates. Failure rate data and sil standards are constantly evolving. Keep your data and knowledge up to date. Regularly review and update the sil verification analysis. Silsafedata specifics. Understand the specific features and limitations of Silsafedata, if you are using it. Learn how to effectively use the software to retrieve, compare, and analyze failure rate data. Understand how it handles uncertainty in failure rates. How to adapt the example for real-world usage. 1 data access * replace get _ failure _ data _ source 1 and get _ failure _ data _ source 2 with functions that can actually retrieve data. This might involve *API calls * if Silsafedata or another data provider offers an API. Use Python's requests library to make API calls and retrieve data in JSON or XML format. Parse the data and convert it into a pandas data frame. Database queries * if the data is stored in a database, example SQL Server, MySQL, use a Python database connector, example pyodk, MySQL connector Python, to execute SQL queries and retrieve the data. File parsing * if the data is stored in files, example CSV, Excel, use pandas read _ CSV or read _ Excel functions to read the data into a data frame. Ensure the file format is consistent and well defined. 2. Error handling * add robust error handling to the data retrieval functions. Catch exceptions, example network errors, database connection errors, invalid data formats, and handle them gracefully. Provide informative error messages to the user. 3. Data validation * validate the retrieved data to ensure it is within acceptable ranges and consistent with expectations. Check for missing values, incorrect data types, and invalid values. 4. pfdavg calculation * replace the simplified calculate _ pfdavg function with a more accurate calculation that takes into account the SIF architecture, diagnostic coverage, proof test coverage, and other relevant factors. You can find more accurate equations in standards like IEC 61508 and IEC 61511. 5. Uncertainty analysis * consider the uncertainty in the failure rate data. Failure rates are often expressed as ranges or distributions. Use statistical methods, example Monte Carlo simulation, to propagate the uncertainty through the PFD calculation and obtain a range of possible pfdavg values. 6. Reporting * generate a comprehensive report that summarizes the SIL verification analysis, including the data sources, assumptions, calculations, results, and conclusions. The report should be clear, concise, and well documented. This detailed tutorial provides a solid foundation for understanding and applying Silsafedata's failure rate comparison functionality, or simulating it, for SIL verification. Remember to adapt the code example to your specific data sources, SIF architecture, and SIL requirements. Good luck.